Hello students, welcome to my channel Engineers Academy. Kindly subscribe my channel if you haven't subscribed my channel yet. Now let's solve this problem. In this problem it is said that one of the three landing pads for a proposed Mars lander is shown in the figure, right? So it is one of the three landing pads, right? And it is said that as part of a design check on the distribution of forces in the landing struts, compute the force in each member of the strut AC, BC and CD, right? So we are required to find the forces in these three members of this landing pad, right? So if we represent those forces, so there will be one force which will be from this point C to A, right? Then there will be another force which will be from this point C to B, and similarly there will be one force which will be from this D to C, right? So let's say that this is that force that is from D to C, right? So we have these three forces. So let's say that this force is FCA, and let's say this force is FCB, and let's say this is FDC, right? So we can write that this is FDC force, right? So we are required to find these three forces, right? And it is said that the arrangement is symmetrical with respect to the XZ plane, right? So this is the XZ plane, so the arrangement is symmetrical, right? So if this distance is 300, so then this distance is 300 as well, right? So this whole system is symmetrical about the XZ plane, right? And it is said that the mass of the lander is 600 kg, right? And it is said that assume equal support by the pads and consult table D2 in Appendix D as needed, right? So the center of the acceleration due to gravity at Mars is 3.7 meter per second square, and since this is one of the three landing pads, so the mass will be equally distributed at three pads, right? So here we will have one reaction from the ground, and that reaction will be acting vertically upward, right, along the z-axis, right? And this reaction will be equal to 1/3 of the total weight of this lander, right? So the total mass is 600 kg, so this will be m times g, so 600 into g, so g is 3.73, right? So this will be the reaction in newtons. So the reaction at one landing pad from the ground is equal to 746 Newton, right? So now we know that this R is 746 Newton and it is acting in the Z direction, right? Now if we find the components of this FCA, FCB and FDC, right, so then we will be able to find the magnitude of these three forces. Then we will be able to apply the equilibrium condition, right? So now if we find the angle of these three forces with one of the axes, so then we will be able to find their components, right? So if I draw a line from this point A exactly vertically downward, right, if this line is parallel to that z-axis, and then if I join this C with this point A, so then we can locate that, let's say that this angle is theta, right? And this FCA will be making, let's say, alpha angle with the ground, right? So this angle will be alpha, and this is the angle theta of this component with the x-axis, right? So now if you want to find this theta angle, right, so then we can use this triangle. We can use the triangle on the ground, right? So let me remove this alpha. We can find this theta from this triangle. If I join this triangle, right, so this triangle, so now if I draw the triangle, we have this triangle, right, and this is that theta, and this length is how much? So this length is 300, this is given, right? So we have this 300 length, and this distance is 550, right? So we can write that this is 550, right? So from this we can find theta. So then theta, in this triangle we can apply tan theta, so tan theta will be equal to perpendicular, so this is perpendicular divided by base, and theta will be equal to tan inverse 300 divided by 550, right? So this will give us the theta, right? And similarly then we can find alpha as well, right? To find this angle alpha of this force FCA with the ground, right? So this angle is, let's say, alpha. So for this, to find this alpha, we will use this triangle, this standing triangle, right? One triangle is lying on the ground and the other one is this standing triangle, and let's say that this point is A dash, right? And let's say that this is the origin, let's say this is point O, right? So this was that OCA dash triangle, and to find this alpha, we will consider this ACA dash triangle, right? This standing triangle. So to find this alpha, first we need to find this CA dash length, right? So we can use Pythagoras theorem, so we can find this CA dash length. So then CA dash square will be equal to 300 square plus 550 square, and to find this CA dash, we will take the square root. So this will give us CA dash length. So this CA dash length equals to 626.5 mm, and this theta is 28.61 degrees, right? So now to find this alpha, we can again apply tan alpha, and this time tan alpha will be equal to this AA dash. So this AA dash length is 350. So we will write 350 divided by the base of this triangle. So the base of this triangle is CA dash, which is equal to 626.5, right? So we will write 626.5, and alpha will be equal to tan inverse 350 divided by 626.5. So now this alpha equals to 29.19, right? So now we can find the three components of this FCA force, right? Now once we know this angle theta and this angle alpha, we can resolve this FCA force into its components, right? So if we first find the component of this FCA force on the XY plane, right? So we will have this component of FCA. So then this component will be the FCA cos of alpha component, right? As we have learned, right? So this will be FCA cos of alpha, right? So cos of alpha, we know alpha. And now if we find the component of this FCA in the X direction, so we will have this component, right? So this component will be the cos component of this FCA cos of alpha, right? So if we write that FCA component in the X direction will be equal to this FCA cos of alpha, and we know alpha, which is 29.19, and then the cos component of this will be the component of this FCA in the X direction, right? So we will write cos of theta, and theta is 28.61, right? So this is the theta. And now if we want to find the component of this FCA in the Y direction, right? So we will have this component, right? And this one will be the sine component of this FCA, right? So we can write that this is FCA along Y. So then this will be FCA cos of 29.19. This component will be the sine component of this this component, this FCA cos of alpha, right? So we will write this is sine of 28.61. And similarly, FCA component in the Z direction will be the sine components of this FCA directly, right? So we will write that this will be FCA sine of alpha, right, directly, right? So we can draw that component which will be acting in the positive Z direction, right? And we can place this component here, right? So this is, from this triangle we can say that this will be the sine component, right? So this is the sine component, sine alpha, and sine of alpha angle is 29.19 degrees. And similarly is we can see that this FCB and this FCA, both of these forces are symmetrical about this XZ plane. So both of these will have the same components, right, but in the opposite direction, right? So if we write the FCB component in the X direction, so then this will be FCB cos of 29.19. The magnitudes will remain the same, only the direction will matter, right? So as we can see that this FCB is again acting in that same direction, so then this is the component of this FCA. So FCB will have the same component in this direction, right? So we can write that this component of FCA is acting in the negative x direction, so we can write that this is acting in the negative x. So we can write that this is acting in the negative I direction. This FCAY is acting in the positive y direction, so we can write that this is acting in the positive j direction, and this component is acting in the positive z direction, so we will write plus z, right? And similarly, if we consider the components of this FCB, so again its one component will be acting in the negative x direction and will have the same magnitude, so we can write that this is FCB cos of 29.19 cos of 28.61, right? The angles will also remain the same since the dimensions are same on the both side of this xz plane, right? Similarly, we can write that FCBY, the y component will be in the opposite direction. The FCB is going away from this xz plane, right? So this means that the FCB will have one component which will be acting in the negative y direction, right? So we will write minus, the magnitude will remain the same, so we will write minus FCB cos of 29.19 sine of 28.61 j. And similarly, the component of this FCB in the z direction will remain the same, right? So it will be also acting in the positive z direction, right? So we can write that this will be FCB sine of 29.19, and this will be acting in the positive z direction, right? So only the y component of both of these forces are acting in the opposite direction, right? Since one force is acting in this direction and one force is acting in that direction, right? Now we will find the components of this FDC force, right? So if I draw a line parallel to this z-axis is this x-axis is, if we draw a line here parallel to this x-axis is, and then if we draw one another line parallel to this z-axis is, right? So we can see that this FDC force is in the xz plane, right? So it will have two components, right? This FDC force will have two components, and one of the components will be acting in this direction, right? This FDC will have one component in this direction, and it will have one another component in this direction, right? So to find these components, first we need to have this angle. Let's say this angle is beta, right? And let's say that this point is D dash. So now we can consider this C D dash D triangle to find this beta, and if we apply tan beta to that triangle, so tan beta will be equal to this length. So this length is equal to 550, this is given, right? So this is 550 divided by this CD dash length, right? So this CD dash length is 350 plus 550 plus this 300, right? So this whole length is 1200. If we add this 350 plus 550 plus 300, so this is equal to 1200. And then we can find beta by taking tan inverse. So tan inverse 550 divided by 1200, right? So this will give us that beta angle. So this beta angle comes out to be 20.56 degrees, right? But one thing is that this point D is at a distance of 100 mm from this z-axis, right? So then this distance is, the overall distance is 550, so then this distance is 550 minus 100, right? So we will write this 550 minus 100, so then this will be 450, right? So 450 divided by 1200, so then according to these dimensions this beta is equal to 20.56. So now once we know this beta, we can find the components of this FDC, right? So the FDC, and this component of this FDC is acting in the positive x direction, and this is the sine component if we consider this beta, right? So this will be FDC sine of beta, right? So beta is 20.56, and this is acting in the positive x direction, so we can write this is positive I, right? And similarly this component which is parallel to the z axis, so we can write that this is FDC along the z axis, and this component is acting in the negative z direction, so we will write minus, and this will be FDC cos of beta, right, since this is the cos component according to this beta, right, so this is cos 20.56, and this is acting parallel to the z axis, so this is negative k, right. And since this FDC is in the xz plane, so there will be the FDCy component is 0, right, so there is no component of this FDC force along the y axis, right, so FDCy is 0 j, right. Now if we apply the equilibrium condition, so if we apply the summation of forces along y axis is equals to 0, so now as we can see that only the component of this FCA and this FCB, they are acting in the y direction, right, so we can see that one of the component of this FCA is acting in the positive y direction, and one of the component of this FCB is acting in the negative y direction, and both have same magnitude, right, so this means that we can write that FCA y, which is acting in the positive y direction, and the other one is acting in the negative y direction, right, so this is FCBy, and this will be equal to 0, right. So now if we write the magnitude, so then the magnitude of this FCA is FC, or from this equation we can say that FCAy is equal to FCBy, right. So now if we write the magnitudes of both of these, so everything will cancel out and we will be left with FCA equals to FCB, right. So this means that both of these forces are equal since they are symmetrical, right, about this xz plane, right. So FCA and FCB forces are equal, right. And now if we apply the summation of forces along the z axis is equal to 0, so now as we can see that this is acting in the positive z direction, so we will write FCAz, and this is in the positive z direction. This one is also in the positive z direction, so we will write plus FCBz, and this reaction is also acting in the positive z direction, so we will write plus R, and minus this FDCz component is acting in the negative z direction, so we will write minus FDCz component, and this will be equal to 0. So now if we write the magnitude of both of these, so FCAz is this component, so we can write that this is FCA sine of 29.19 z, and similarly FCA and FCB are equal, right. So this is again, if we substitute FCB equals to FCA, so then this is FCA sine of 29.19, and so this means that if we write this as FCA sine of 29.19, and if we add both of these, so this will become twice, right. So we can write this 2 times FCA sine of 29.19 degrees, right. And similarly plus R, and this R is 746 newtons, so we will write plus 746 newtons minus the Z component, right, the Z component of FDC, so this is minus FDC cos of 20.56, right. Or if we consider all the positive signs, so then we have written those negative signs here, right, so then we will just add all those components, right, in the Z direction, so this will be equal to 0. Now when we simplify this, so we get this equation 1, right, and now if we apply the summation of forces along x equals to 0, so again we have this one component FCAx in the negative x direction and FCBX in the negative x direction, right? So we will write FCAX plus FCBX, right? And we will consider the signs, right? So this is acting in the negative x, this is again acting in the negative x, and similarly this component is acting in the positive x direction, right? So this is FDCX, right? So we will write plus FDCX, and this will be equal to 0, right? So now we can write that this is minus FCA from here, right? So this is cos of 29.19 cos of 28.61, and again both of these FCA and FCB are equal, so then we can say that this will be twice of this, right? So minus 2 FCA cos of this thing plus FDCX, right? So this is FDC sine of 20.56, and this will be equal to 0, right? Now when we simplify this, so then we get this equation. From this equation we can write that this is minus 1.533 FCA, and this will be equal to minus 0.351 FDC, and this will be cancelled out, and FDC will be equal to 1.533 divided by 0.351 FCA, and from this we get FDC equals to 4.368 FCA, right? So now we get this relation. Now if we substitute this FDC in this equation 1, so then we can write this equation 1 like this. So then this will be 0.975 FCA minus 0.936 into FDC. So FDC is 4.368 FCA, and this will be equal to minus 746, right? And now if we take FCA common from this, so then we will get this equation. This will be 0.975 minus 0.936 into 4.368 FCA, and this is minus 746, and if we divide this minus 746 by this whole term, so then we get FCA equals to 240 newtons, right? So this is the magnitude of the force in the CA member of this landing pad, right? So this is that FCA force, and since we know that FCA is equal to FCB, so then we can write that this is also equal to FCB, and from this equation, let's say this is equation 2, so from equation 2 we can find FDC force. So FDC is 4.368 into this FCA, which is 240, right? So then we get FDC equals to 1046 newtons, right? So now we have determined the forces in each member of this lander, right? This lander pad, right? So this is the solution of this particular problem.